Okay, we're going for the last forms, the last ways we can calculate enthalpy. Everything good to go? Okay. We're going to do Hess's law on bond energy. So thus far we have calculated enthalpy using stoichiometry, calorimetry. There's one more in there. I don't know. Some other way that I can't. From the charts. There we go. From the charts, we're going to do Hess's law and bond energies. Go ahead and circle bond energies one more time and write weirdo. Okay. So in Hess's law, we're making use of the fact that enthalpy is a state function. That means it doesn't matter how we get there, the end result is the same. So I want you to look at this reaction, and then we'll go back to the steps and the definition. Let's say we would like to know the enthalpy for the formation of 1 mole of carbon monoxide. And we look it up in the charts, and there isn't a change in enthalpy for this. But there was a reaction that looked like this with an enthalpy, and a reaction that looked like this with an enthalpy. You can take these two, what I call elementary reactions, and manipulate them so they add up to this target reaction. And that is okay, and the enthalpy you calculate from doing that will be absolutely acceptable because of Hess's law and the fact that it is a state function. Now what you're going to do to manipulate these is you have a couple of choices. First, you can leave this reaction as it's written, or you could flip the reaction and make the CO2 the reactant and the C and the O2 the products. If you do in fact flip the direction of the equation, you need to flip the sign of delta H, so it would become positive 393.5 kilojoules. You could alternately flip these. You can multiply the entire equation by an integer to give you the correct coefficients if you would like. If you multiply by an integer, you also must multiply delta H by that same integer. And you can also multiply any equation by a decimal. Likewise, delta H will be multiplied by a decimal. And then when you're done, you add up the elementary reactions, and they should come out to the target reaction. One of the things that you'll make use of is the fact that anything on both sides of the arrow that look exactly alike are spectators, and you cross them out. So I think I just took care of all of this. Let's get to this part, which is kind of easy. All right. So when I look at my target reaction, I'm doing so while I'm looking at my elementary. And I see in my elementary reaction I have carbon and oxygen as reactants. And I want carbon and oxygen as reactants in my target. So I'm going to write this reaction and leave it exactly as it's written. Now I look at this one. This is carbon monoxide as a reactant, and in my target I want carbon monoxide as a product. So I'm going to flip this one around. CO2 will be the reactant, carbon monoxide, and 1/2 oxygen will be the products. So I'm going to flip the sign of delta H as well.
Were you looking at the second reaction?
Yeah, this one, the second elementary, and seeing how it stacks up to the target. Okay. I look at the coefficients of all of these and I think, you know what, I don't need to change anything, so I'm ready to add these together. I will likewise add the values of delta H together to get the delta H of my target reaction. Okay, C does not appear on this side, it stays. oxygen, I have 1 mole of oxygen here and half a mole of oxygen here. This half mole of oxygen will cancel out half a mole of this oxygen. And I see CO2 exactly the same on both sides of the equation, so it cancels. I believe I'm ready to add carbon plus 1/2 oxygen yields carbon monoxide gas. This matches this, so I know I'm correct. And when I add these two values up together, the delta H of my target reaction is negative 110.5 kilojoules per mole. Get it? It's nice and easy.
How'd you get 1/2?
There was 1 oxygen and half an oxygen. It was written that way. Right here, there was 1 whole oxygen here, and there was a half an oxygen here. Half an oxygen was canceled.
Oh, okay.
The delta H's are always given, right?
Yeah.
Yes, for the target, for the elementaries, yes. Okay, here is our second one. Calculate the delta H for the reaction. 2 carbons plus H2 yields C2H2. Here are our elementary reactions. The first thing I'm going to do is determine whether I would like them to be as written or go in the reverse direction. For our first one, I see it has C2H2 as a reactant, and I clearly see C2H2 as a product. So I'm going to go ahead and flip this one right off the bat. CO2 plus H2O. Remember, the state of matter matters, so it is important that you note that you have liquid water. This and this yields 5 seconds, 5 halves oxygen gas. And since I flipped this equation, I will flip the sign of delta H. All right, now looking at the second elementary reaction, I see that I do want carbon as a reactant, so I'm just going to leave that one as written. And for my last one, I do want liquid water as a product, so I'm going to leave this as well. Okay. Now, I look around here and I think, okay, I have the correct number of moles of C2H2, so I'm probably going to leave the coefficients alone here. I look here and I see I would like 2 carbons, so I'm going to multiply everything by 2. So this would be 2, 2, and 2, and I'm going to multiply this by 2 as well. I'm going to make that actually look like a 2. Okay. What about this? H2 looks good as this is now, doesn't it? So I think I'm ready to see what happens and try adding the whole thing up. All right, looking for things to cross out, I see this and this. I see this and this. I want this to stay, I want this to stay. Uh-oh. Are they equivalent?
Yeah.
Okay, everybody who's past 3rd grade can see this could be if you were to make this look like this, it would be 4 over 2. 4 over 2 and 1/2 is 5 over 2. So they are gone. And you would come up, when you added everything together, with and you add all of these up, reminding yourself you multiplied that by 2. Who clickety-clacked their computer or their calculator already? Because I don't think I have the right answer.
How'd you get rid of all?
I think I got 226?
Yeah.
Is it the same thing as 4 over 2?
226.81 kilojoules. That is absolutely correct. Thank you for the answer.
How'd you get rid of all this O2?
Okay, so you had 2 O2s on one side and 1/2 of O2 on the reactant side. You have 5 over 2 O2s on the product side. Another way to write this is 4 over 2. 4 over 2 plus 1/2 is 5 over 2, so canceling, canceling. Okay, turn your paper over. I'm only going to do the last part, so and then you can practice. We'll practice the other ones together. I want to skip to bond energies. These are covered in the pencast, which is now right. So I wanted to talk about the weirdo bond energies. And you know what? This is going to help those people who are kind of irritated by the whole solution thing yesterday. Remember, like, how could you tell energy was released or absorbed? This will make you happy. All right, first of all, you have to, this is the final way to calculate enthalpy. This is the final way to calculate enthalpy, and you need to make 2 assumptions here, and they happen to be correct. Energy is absorbed when bonds are broken. What that means, if you have my favorite equation, in order to get A and B ready to change into C and D, you have to add energy to break the bonds that are holding A and B together, right? Now, energy is always released when bonds are formed. So when C and D are formed, energy exits. Okay. If more energy exits, if more energy is released when the bonds are formed than took to break the bonds in the reactant, then the entire delta H of reaction is exothermic. Do you get that? If I had to add more energy to break the reactant's bonds than was liberated when the product bonds were formed, it would be an endothermic reaction. Got that? So delta H, when you're talking about bond energies only, is equal to the bonds, the energy of the bonds broken minus the energy of the bonds formed. That would be the reactants minus the products. That's why it's a weirdo. The reactants minus the products. Where do you get the bond energies from? The table. And you have to actually draw the bonds between all of the reactants and products so you can figure out what's going on. So my balanced equation is H2 plus F2 yields 2HF. What I'm saying is this H2 bonded together, F2 bonded together, yields, understood? Now, remember we're doing reactants minus products to give us the delta H of reaction. I have HH, the bond energy needed to break an HH bond when it's reacted is 432 kilojoules. The bond energy needed to be inputted to break the FF is 154 kilojoules. The bond energy released when HF forms is 565 kilojoules. There are 2 of them. So, 432 plus 154 minus 2 times, whatever that is, 565 is,
We get 500.
534?
544.
544 kilojoules per mole.
Negative 544.
Yep. Negative 544. So what this is saying is, what? It's exothermic. More energy was released when the HF bond formed than was required to break the HH and the FF. Isn't that just nice and sensical? Why couldn't all of life be sensical like that?
Exothermic.
It is exothermic. Okay, now this is where things get kind of crazy. Look, what would you do if you had a molecule like that? You don't know. You draw it. There would be 3 CH and 1 CCl.
Was this on yesterday's homework?
Yep, that's why you're seeing it now. Why do you need to draw it? So you know the bonds. It gets, it's just an easy way to do that. Okay, now